Um, Good morning. My name is Nigreisy Montalvo. I am a PhD candidate at Institute Imagine, located in Paris, here in France. And today I'm going to be presenting a work that we are conducting in the lab on the use of federated learning for the pathogenicity scoring of genetic variants across independent institutions. So before getting starting, I think it is very important to give a couple of definitions in order to understand the scope of our project. That's why, firstly, I will describe what classical machine learning is, and I will present the limitation of this approach in a multi-site clinical setting where protecting data privacy is mandatory. Lately, I will introduce a technique that can help us to overcome this problem of machine learning in this setting, which is called federated learning. And by the second half of this presentation, I will present our use cases, which are federated learning simulation studies for the clinical interpretation of copy number variants and single nucleotide variants. And we will also compare centralized and federated learning approaches. So what is machine learning? In a few words, machine learning is the use of mathematical models and input data to make a machine learn. Learning in this context means that the mathematical model is going to be able to find patterns in the data, correlations among data points, some kind of representation that will allow the model to make a prediction in the future. In machine learning, we call the input data the training data. And it is important to say that the mathematical model is not explicitly programmed. So in machine learning, we define two phases. The first one is the learning phase where all this process of learning happens, we call training, and we get as a result a machine learning model that is ready for the second stage. In the second stage, called the inference phase, we give to our machine learning model a new unseen data point, and thanks to what it learned in the past, the model is able to make some kind of prediction. Now imagine the following situation. Imagine that we have 4 institutions, clinical institutions, that they want to collaborate for training a machine learning model because they are interested in doing some kind of prediction about a very specific disease. So if we would like to do the machine learning in the traditional way, we will have to move the local data set to a central server and then do the training process. However, in practice, in most of the cases, this is not possible because there are regulatory constraints that do not allow the sharing of clinical data because clinical data is very sensitive and should be kept private. So how do we do? How can we do machine learning in this setting with decentralized and private data? And here is what federated learning comes to the rescue, because federated learning allows us to do machine learning in this situation. If there is just one key idea of federated learning that you take home today, is that federated learning follows this principle. Instead of bringing the data to the model, we can bring the model to the data. And you're going to understand why in a few seconds. So federated learning works like this. You have your institutions that we are going to call clients, orchestrated by a central server. A central server is going to define a machine learning model, for example, a neural network architecture, and it's going to send to the client a copy of this model. In the case of neural network, it's going to send the weight of each layer. The clients are going to use this model obtained from the server and their local data sets for doing local training during several epochs. And once they're done, they're going to send back to the server the updated of the model. The server is going to do some kind of aggregation in order to build a new instance of a global model. The simplest one, for example, is taking the average of the weight in the case of a neural network. And this is a process that is going to be repeated by several rounds. By the end of federated learning, each client is going to receive a copy of this global model that was trained using the decentralized and private data. The federated learning has a lot of benefits. The first one is that it increased data privacy and security because the private data is never shared. It enhanced data diversity because thanks to these techniques, we are able to train a machine learning model using data coming from different sources that lead to the increases of model accuracy. And there is a characteristic of federated learning that I really like, is that it's more flexible than classical machine learning because we can add new data points or new clients on the fly without the need of retraining the machine learning model from the very beginning. So now we have the basic to follow our use cases, which are federated learning simulation for the clinical interpretation of copy number variants and single nucleotide variants across independent institutions. If you remember for federated learning, we need to define a global machine learning model, the way we aggregate the model, and the training set. So here we're going to see the first two one. As a machine learning model, we try multi-layer perceptron and a neural network architecture that is inspired in random forest that is called shallow neural decision forest. The reason why we chose neural network architecture is because most open source library of federated learning, they need the model to be a neural network in order to do the aggregation. So we use the leave one chromosome out approach for training the model in order to avoid bias. And in the end, we were training a bundle of 23 independent classifiers, one per chromosome. In order to be fair in the comparison between centralized and federated learning approaches, we did a hyperparameter tuning of the centralized model, and we used this model in the federated learning setting. For federated learning training, we tried different aggregation techniques, hyperparameters related with the way we aggregate the weight, and some training configuration, like, for example, taking the 50% of client in each round, analyzing the use of patch normalization layer or not, and we were implemented early and stop it for preventing overfitting in federated learning. We also did a decentralized evaluation in each round, and by the end, we tested 50 different evaluation settings. We implemented these simulations using Python and Flower, which is an open source library for federated learning. Our first use case was federated learning for the clinical interpretation of copy number variants. And for this, we base our experiments in a supervised machine learning approach proposed previously in the lab called CSV score. I don't have the time for going into the detail, but if you are interested, you can follow the link. But CSV score basically is a supervised machine learning approach that, given a copy number variant, is able to give a prediction of whether it is pathogenic or not, taking a set of features as description. So this is the part where we prepare our data set for doing the federated learning. And for doing federated learning, we need to split our training set in different data owners. In order to have a very natural split in the process, we use CleanVar, which is a public database that contains curated information about genetic variants and the clinical interpretation. And it was interesting for us because CleanVar has a field named submitter that allow us to identify which was the institution that submitted this commitment variant or single nucleotide variants to the dataset. Following this workflow that is present, we were able to identify a training set consisted of 8 data owners and 2 independent tests for assessing the performance of classifiers. Before going into the detail of the results, I want you to take a look to this graph that shows the distribution of records per data owners in these experiments. We can see that is a data owner called Invitae that possesses the 82% of the data, and the other data owner, they had so much little data. So because if we do the experiments and we include Invitae, the experiments will be completely dominated by Invitae. We decided to exclude it in this experiment. And at the same time, we were interested in seeing if a collaboration among the smallest data owners could compete with the largest one, Invitae. And these are the first results for the model multi-layer perceptron. Here, I want you to distinguish 3 blocks. The first one is the model trained by Invitae. The second one is the centralized of smaller data owners. And the other ones are the federated learning strategies. Here you can see that with federated learning, with the technique FedProc, we were able to reach competitive results with the centralized model. And this is a tendency that we also observe with shallow neural decision forests. It is important to say that, for example, with the smallest data owners, there were data owners that didn't have an example of each chromosome, so they couldn't implement the leave one chromosome out approach. But when we were doing federated learning, we were able to get a training set consisting having a sample of each chromosome. So our second use case is for single nucleotide variants. We follow the same baseline. In this case, we base in a supervised machine learning approach proposed by Emilio Capriotti. And this is the paper if you're interested, but basically is the same approach as CSV score. We want to classify single nucleotide variants into pathogenic or not pathogenic. We follow a workflow as previously described, and we were able to identify 6 data owners for the training set and 2 independent test sets. Here, the distribution of the client is not so complicated as the first one. So we wanted to assess this scenario. And in this scenario, the data owner didn't have the same amount of pathogenic and non-pathogenic variants. That's why we decided to do undersampling of the majority class. Here are the results of our experiment for multi-layer perceptron. And here they are different blocks. The first one is the centralized, taking the data of 6 data owners. Then we have the independent classifiers. And then we have the federated learning approaches. Here we saw that we can see the federated FedProc was able to outperform the performance of centralized and individual data owners. And this is a tendency that was also repeated for shallow neural decision forests. So summarizing the results that we obtained, we could see that in the legends copy number variance, the federated learning of a smaller data owner reaches competitive performance with the centralized data model counterpart, and even didn't reach the performance of InVitae. We can say that it was kind of competitive because the smallest data owners didn't have so much data in comparison with InVitae. And for the coding single nucleotide variants, we saw that the federated learning approach was able to improve the performance of centralized and individual model. So as feature perspective, we aim to analyze if the heterogeneity of copy number variants and single nucleotide variants dataset could explain the result in the federated learning setting, or whether it is related to the statistical distribution of the data. Federated learning can outperform the decentralized. And we want to simulate the simulation for not coding single nucleotide variant. I would like to acknowledge to the contribution of this project. Thank you.
Thank you. We can take a question while the next speaker is setting up. So please. So any question? Okay. So make it brief, please, and let the people access the computer.
Thanks for the nice talk. Is it possible to guarantee that you won't be able to guess anything from people within each institution just from the weights that they give you?
Sorry, can you repeat?
Sorry. Is it possible to guarantee that you won't be able to guess, for example, that this many people have this particular SNP in one institution just from the weights that they give you? Can you guarantee that?
We need to do like more specific analysis. I cannot guarantee, but maybe if we analyze like in the federated learning, for example, the loss function that they are returning, maybe we can get something.